And last time we talked a little bit about moment of inertia. If I could, I'll remind you of the moment of inertia equation. Here it is for this exact one. It was something like x squared dm. Where did that come from? If I could scroll up even further, for a single point mass, the definition of moment of inertia is mass times distance from the axis squared. Again, it's a mass. That's this little ball here. It's the ball's mass and the distance from the axis squared. That's the key thing here. So if I go back to this page, this is now page 60, we could see that what I'm trying to do is trying to take this entire shape, this entire triangle, and split it into chunks of mass which are equidistant from the radius. Every point in that chunk has the same distance or the same radius from the axis, the dotted line. By doing that, all I'm doing is essentially saying, hey, I'm taking x squared dm for a point mass. Dm would be a small amount of mass. And then I'm going to keep adding it up. And when I finish it, I get the total moment of inertia. Okay, so let's go into our particular problem now on the page 10.13, page 61. So you could already see what we're going to try to do here. And then we'll see, hopefully, something in the mathematics that help this out. So here's my radius for some arbitrary slice. And so I'm going to choose this type of slice. Why? Because every single point in here is the same distance from the axis. This, let me do a green slice here. This would be a bad slice. Why? Because different points within the same slice have a different radius. That's bad. So, okay. So now in this case, we know we need to somehow characterize this slice. I need the mass of it. If I want the mass of this slice, dm, well, in this case, I think back to my table that's somewhere way back there in the center of mass on page 43. So if you wanted to, you could go to page 43 and look up 1D, 2D, or 3D. Do I use lambda, sigma, or rho? In this case, I'm just going to write it out. This is an area. So I know that this is going to be a small amount of area. The dimensionality of my object, the entire object, is 2D. It's a plate. Okay, it's a plate that's 2D. The dimensionality of my slice is always the same as the dimensionality of my object. If you have a 2D object and you slice it up, you're slicing it into 2D slices. If you had a 1D object like a rod, then this would be a 1D slice. The point of this is if you have a 2D object, you should have a dA. And if you have a dA, you need a sigma. Okay, that's supposed to be sigma. All right, so got it. In this case, I'm going to pop over to the solution and see if this makes sense now, okay? And if you have any questions, dump them in the chat and I'll catch up in a minute, okay? If you have any questions, dump them in the chat. So that said, where is my solution? There. Oops. Okay, so this is a perfect time to go over. How do I get what sigma is? Well, if it's a uniform plate, which I believe it was, let's go look. Uniform. Because it's uniform, this is what allows us to say the following. If it's uniform, sigma is that. If it's uniform, that is true. Because uni. All right. So because that's uniform, well, now this is pretty easy. That's the area of the triangle. That's the mass of this particular triangle. So flipping that 2 up top is pretty straightforward. All right. Ignore this comment, whatever. We don't need that right now. Okay. So now let's go back to my picture. Whoops. And I'm going to go back to the problem statement. So now, okay, we figured out sigma for this thing. So sigma, we've got it. Now I need to figure out my slice. Well, the slice is going to have some height, y, or maybe you want to call it h, I don't know, whatever you want to call it. We could call it y is the height. And then it's also got some thickness. And in this case, it's a small amount of distance in the x. I'm going to call that dx. So this gets us the height, the area of my slice is going to be y dx. All right. And so all I have to do is figure out this function for y. Well, because that's a line, hopefully you see this. You could think to yourself what it should be. I'll go over there. Whoops, that's the wrong one. This one. The height of the slice should be rise over run, which is negative because it's going downwards, times the horizontal coordinate plus the intercept. And you could rearrange that a little bit. That's kind of pretty. All right. So now the mass of a particular slice, that's sigma dA. We've got the sigma, we've got dA. You plug it in and do some math. All right. And hopefully that's not too bad. And let's stop for a second and see if there's any questions in the chat. Okay. All right. And let's see. Problems upon problems of homework. Okay. Yeah, so sorry about that, Ma. I just got your question now, and my apologies for seeing that now. Hopefully, let's take a look at the schedule and when your test is, because right now it's April 8th, right? And I believe your exam is on 4/20, your favorite. Let's see here. And yes, there are a lot of problems. It's just problems upon problems. Oh my gosh, really? Okay, let me stop my share for a second. Okay, there it goes. Sorry about that. Okay, so when I go to the modules, let's just take a look where we're at. I believe the test is on 4/20. Yeah, so where should you be? We want you guys to be done with chapter 10 problems before this exam. So we've got all this week and I believe all next week to get done with chapter 10. So if you look here, this is just chapter 10, and that's it. So chapter 10 is oppressive. But yeah, this is why I've been saving time. We've got this week and next week to get all the way through chapter 10. So hopefully you're maybe finishing up chapter 9 about now. Whoops, I lost my chat. Where did it go? I saw there was a, okay, let me get back to this. Okay, so Ma, hopefully that addresses your question. Hopefully you're done with chapter 9 and started chapter 10. If you're just finishing up chapter 9, that's cool, but chapter 10 is a monster. You got to get on chapter 10 pretty soon. Regarding Nate Dogg, yeah, so the practice test, that's a good question. If we want, let me go take a look there. So if I wanted to look at the practice tests, whoops, let me hit my screen share button. Sorry about that. And then I got, okay, so if I could look at, (161) exams. So hopefully you could see that a little bit. So Nate Dogg's question, notice he's saying, hey, these ones only cover 5 through 8, and these ones cover chapters 9 through 12, and we're supposed to be doing chapters 5 through 10 this time because of this weird COVID stuff. So I think, Nate Dogg, what might be easiest is maybe I'll look through the first 4 or practice tests from here and tell you which problems are good practice. if you want, you could start looking at some of these as well. And these are going to look pretty scary, but let me make this a little bigger. And to be clear, you're going to get an equation sheet that looks something like this, where you've got those moment of inertias. Great question. But so that's chapter 12. That's chapter 11. Chapter 11. That's chapter 9. That's chapter 10. That's chapter 10. And this is probably, let me see. Yeah, this is the chapter 10. So what I could do is try and go through and maybe identify some problems. And I'm going to stop the screen share for a second and see if that addresses Nate Dogg's question. Yeah, so let's see. Okay, so that's a great thing I can do. So that's on my list of things to do. I'll try and do that. And that will help you study for the final as well, right? So whatever. Although the final is comprehensive, so whatever. Yeah, yeah, it does seem a little bit scary. And so it's the kind of thing where the first time you're going through it and just getting those homework problems done, it could feel just brutal. But then when you go back and do the review for the tests, it's hopefully hopefully will get a little bit easier. A lot of times the material starts to get a little bit more technical, which means the problems are not nearly as clever or creative. So a lot of times what that means is a student who's willing to just grind should have less trouble because there won't be some weird giant conceptual leap. I hope, fingers crossed. Yeah, because it's a lot of just kind of, can you get done with a lot of practice and do some technical? It doesn't seem, it is scary. Yeah, right on, right on. All right, well, yeah, the more questions you can ask me, the Tuesday office hours don't get a lot of people coming in. So Mom, maybe you could maybe check that out, and I could try and help you more there. Yeah, and the labs are designed to help you with that too. We're doing calculus center mass in the lab this week in a way that hopefully will make that more intuitive. All right. Yep. That said, we should probably get to another problem, and so I'm going to start plowing ahead and try and help you. All right. All right. Sounds good. Let's see. The more we do here, hopefully, the more helps you out. Let me get out of there. Let me get out of there. And let's go back to here. Let's take a second to see here. I'm going to look at 10.14. 10.14. And I want you to think, it's been a few minutes now. See if you can think how to set this one up. I'm going to give you a minute. I'll look at my clock here. Okay, so we'll start up at 4:49 on this problem here. So take a second to think if you know how to set it up. What would you write down? Part A is pretty good too. You could think to yourself, should the moment of inertia be bigger or smaller than a uniform rod? All right, so there's a minute. I'm going to go ahead and address this. In this case, we see that the rod becomes more dense as you get to the outside. There's more mass out here than there is in here. That's what the picture is supposed to represent. Because I is equal to the integral of x squared dm, in this case, we expect this should actually have more moment of inertia. Or said another way, This rod is like a figure skater with the arms out. This rod is like a figure skater with the arms out. The mass is far from the axis. Whenever you have a mass far from the axis, you have a large moment of inertia. Okay, so that was supposed to be the conceptual part. And then here, in this case, dm should equal lambda times dx. Think about it. In this case, I have a 1D object. It's a rod. We think rods are 1D shapes. So I need a 1D density and a 1D slice. dx has units of meters. This has units of kilograms per meter. We expect this should match up. And so from there, this actually is really easy. It's just stick in the x squared, stick in the lambda in here, stick in the dx, and you should get something like alpha x to the fourth and integrate it. Let's go take a look. Whoops, clear that. So if I go over and look at this one, there we go here. So in this case, oh, I see. Part M was just get the mass. Let me go back and look at that one. Sorry about that. I skipped part. I see. Let's first get the total mass. So when we do the total mass, we don't stick the x squared in there. When you get the moment of inertia, that's when you're going to stick the x squared in there from the definition. So if I go over there, sorry about that. Here, this is how you get the mass. Just integrate dm. There's dm. Stick in what lambda is, piece of cake. Got it. This is cool because now we actually, you're going to see me do this a lot in physics 163. This was a constant in the density. The cool part is, hey, we figured out a relationship between this constant, which has no meaning, and the total mass and the total length. So this is a way to describe that constant. That means anywhere else in the rest of the problem where we see this constant, we can get rid of it by replacing it in terms of things that have substantial meaning, the mass and the length. That's cool. All right, now going down here, here's the center mass equation, or sorry, the moment of inertia equation. We stick an x squared from the definition, that's dm from before, and we get all this. And notice, like I said, alpha was this quantity we figured out right here. That's what allows me to figure out this strange thing. All right. And then let me go back to the question really quick, and then I'll check the chat. So if you got questions, keep dumping them in the chat. Anytime you want, Trey is here. He can answer those if he wants. So in non-uniform problems, oh, if the origin in the figure was at the middle of the rod, oh, that's interesting. So if we had a situation like this, it would actually be a little bit different because the rod would be dense over here, it would be dense over there, and it would be not that dense in the middle, right? And so it would look a little bit different, but we'd have negative L over 2 as this limit and positive L over 2 is this limit. And pretty much that's the only change. The picture would look a little bit different. The integration limits would be a little bit different, but the problem would be exactly the same. Clearing that out, let's go look and see if there's anything else to say about that. That's basically it. Limits change. All right. And now I'm going to stop the share for a second. Okay. It looks like there's no questions, so I might go ahead and keep going through. My goal is to try and do as many problems as we can. It's not the same as in class, but let's try and keep going. So if you have any questions, throw them in there. Let's go and do another one. I'm going to leave 10.15 at home. And I want to get to the parallel axis theorem on the next page. So go to page 62. Page 62. And so I'm looking at the parallel axis theorem. It turns out we're going to use the parallel axis theorem probably more than the calculus, although you don't really understand it until you've done the calculus. So I'm going to get right to it. You can hear by the pickup in my voice, this is kind of a big topic. This is exciting. This is an amazing trick which allows us to avoid doing calculus. And that's fun. We can do more physics when we spend less time doing calculus. Not that I don't love calculus, but let's see if we can understand this one. Okay. So right there is some crazy looking plate. Okay, there's a plate, and what I've done is this red axis is running through the center mass. Let's say for whatever reason, that's through the center of mass. Now this blue axis over here, notice that it is parallel to the red axis. So if Jesse's out there, my bad. But yeah, so there's two axes. And the important part is, I cannot stress this enough, people, it's got to be the parallel axis theorem, not the perpendicular. There is a perpendicular axis theorem, and it's different. Okay. Now, if you have these conditions met, be very clear here. One of the axes is parallel to an axis through the center of mass. Both of these things, it has to be parallel, and one of them has to go through the center mass. Okay. Doesn't just work on any two parallel axes. It's got to be one of them through the center mass. It's got to be that. If you do that, all you need is the distance between them. If you know the distance between them and the mass of the plate, if you know these two things and one of these other two, either this or that, then you can figure out the fourth thing. Mass is usually pretty easy. Distance between the axes is pretty easy. And so it turns out you can do this. Let me give you an example. Why are we doing this? Why care about this thing that I'm so excited about? Well, take a look at this one, 10.16. The first thing I do when I get my test questions is I'm like, okay, how do I do the moment of inertia? I'm going to go to my table. So if I could, I'm going to go to my table. This is my exam equation sheet. Okay, it's a rod. It's a rod. I'm going to go back and look. Whoops, this one. Oh, crap. This is not at the middle, and it's not at the end. This one tells me, okay, if it's in the middle, I use 1/12. If it's at the end, I use 1/3, but I don't know what to do if it's somewhere else. That's where the parallel axis theorem comes in handy. In this case, what you could do is you could say, what we could do is we could say, okay, well, I do know that at the center of mass of a uniform rod, this is a uniform rod, the center mass should be right in the center. If I draw an axis parallel to that, this would be I, center of mass. And from the table we just looked at, I know from experience this number is 1/12 times the mass of the rod times the length of it squared. That is in my exam equation sheet. It's on my chart. That's something I don't need to use calculus for. Well, wait a minute. If I know that, I just need this distance between. Give me a second. If I could figure out the distance between, well, that looks to me like it's maybe L over 2 minus X. Think about it. This whole distance here should be L over 2, right? That should be L over 2. So now I've got all the pieces. Take a look. I know I center of mass. I know this piece right here because I know the mass and I know the length. I know the mass, so I know this. Also, because I know the distance between the two parallel axes, I could shove that right into D. And now what I can do is I can actually figure out this moment of inertia, even though it's not in the table, without having to do calculus. And at first it's going to seem like, why don't I just do the calculus? Trust me, this is good to know. Really good to know. I'm going to pause for a second and see if there's any questions here, and then we can come back to that. Okay. I don't see anything in the chat there. Let's go crank. Let's do this. All right, so I'm going to go to the solution now. So I'm doing 10.16. Let's look at the solution. There's 10.15. That one's worked out for you. So 10.16. This was from the table. This was the mass. That was the distance between the two axes right there. And so I love this comment. All right, I don't know what I was trying to mess with. It's not too crazy. But so notice when we do a little math here, you're going to get a fourth plus a 12th, which I believe is a third. And then there's these other terms. So this one maybe is a little bit easier to plug in. I'm going to go back to the question really quick and see. So it's just a bunch of math and you just write down a bunch of symbols. Great. Then we can hopefully use that to do physics in the last half of this chapter. All right. So now, think, what should the result be when x equals 0? So if x equals 0, let's go look at the table. That's at the left end. I think it should be 1/3. So if I go to my table, which I believe is this one, if x equals 0, it should match this picture right here, right? Think to yourself, that's what it should be. Let's go back and look at it now. Whoops. If x equals 0, that's all the way at the end. What should we get? Well, if x equals 0, these two terms drop out. We get 1/3. Hey, it works. Now you know how you get. That's one way to get this. That's pretty sweet. And then if x equals L/2, then notice you get back the result from the table as well. So that's a way to check that one. All right. So we'll stop the share for a sec. All right. So, all right. And now I think we're ready to go on here. Let's take a look. Let's just go in order here. Let's do 10.17. And let me make a mark here. So we just did 10.16. And we did, I think, 10.13 and 14. Got it. Okay. All right. So let's go for it. And those of you that weren't here maybe right away, one thing you could do is if this is too slow and painful, you could actually go to the live stream and watch it at double speed later. So, or 1.5 speed. So if this is frustratingly slow for you, because I'm slow, I understand. Okay, I see Dane has a question. This may be a dumb question, but why do we sometimes use integrals to calculate and sometimes? So Dane's question is great. Oh, and then Trey's got an answer there. Yes, that pretty much sums it up. I love Trey's answer there. Basically, I try to avoid calculus if possible. The parallel axis theorem, once you get used to it, is super fast. Let me show you something else, all right? So since I've got my screen here, this is an old test question here. So, well, this one, notice there's a pivot point right at the center. You would need the moment of inertia about the center plus the moment of inertia of a point mass. We're going to end up doing that. So notice no calculus required. If I do another problem, here's two different problems. Let me see here. This is a plate. So it turns out in my table, I know the moment of inertia of a plate. I could go up here and say, wait, where is it? Moment of inertia of a plate. I'd have to pick which axis matches better. And then I have to use the parallel axis to shift it rather than do calculus. So think about this, Dane. If you wanted to get the moment of inertia of this table, which is a chapter 10 question, you could take the moment of inertia of a plate about an axis through its center right here. This is in the table coming out of the page. That's supposed to be indicate out of the page. I is something like 1/12 some crap. I think it's mass a squared plus b squared. And in this case, a equals b equals side s. So in this case, now you say, well, how much is the axis shifted? The distance is probably s over √2, I think, or something. And we could go through that more carefully later. But the idea is the I of this particular plate is going to equal I center mass, which is from the table, plus the mass of the plate times side over root 2, I think, quantity squared. And that's a lot faster than doing calculus on that plate. So if you have a uniform plate and can use the parallel axis theorem, it's so much faster than doing calculus. That's what you should do. So let me clear that out and stop the share. So Dane, hopefully that is addressing your question. Yeah, definitely no dumb questions. I agree for sure with Trey. Yeah. All right. Yeah, it's a pretty cool trick to use. All right. So now let's go ahead and look at 10.17, and that's another example of this. So that problem I just looked at showed you why you might care about this. So right now, all we're doing is trying to big picture here. The moment of inertia, is essentially the rotational equivalent of mass. If we want to understand how torque works, we need to understand how mass rotates and how it is affected during rotation. Moment of inertia is a key part of that. So right now, this feels like straight math. And it is. And the idea is it's sort of like when we did vectors. We were doing straight math for a while until we got used to it. And then we used vectors to do something interesting, some forces. Okay. Just like you use calculus and now you can do center mass. Now we're learning how to do moment of inertia so that we can apply it to interesting problems. Right now, it's just math. Okay. That said, consider a uniform sphere of mass m and radius r, this sucker right here. And we've got this unhappy face. And now what I'm saying is I want to put the axis right here instead of through the center. Whoops, that's terrible. So normally the axis is through the center, right? That's a little better. So think to yourself, I want to use the parallel axis theorem. If I want to use the parallel axis theorem, I need this right here. I need the mass. Do I have that? Yes. I need the radius. Okay, that gets me the moment of inertia of the sphere. And in this special case, whoops. In this special case, hopefully you see that the distance right here is just r. And this is very typical for a moment of inertia parallel axis theorem. So if you've already got that in your head, that's cool. I'm going to go look at the solution. The center of mass is 2/5 mr squared. If you're saying, where does that come from, dude? Let me show you. It's exam equation sheet time. That's a spherical shell, like a basketball that's hollow inside. That's not us. Here it is, solid sphere. The solid sphere and the spherical shell, notice it doesn't matter where you throw that axis. Right? It's always going right through there. As long as it's through the center, it will be this. So going back to that solution, that's where I got this piece. 2/5 from the exam equation sheet. mr squared, m was the mass, and the distance between the axes, r squared. Beautiful. Done. That's it. Okay, so hopefully that one was all right. Yeah, and that's the idea is we want this parallel axis theorem to get locked in. I'm going to keep going with it. Let's do another one, all right? Let's go back. This is now, here it's starting to get a little bit more advanced, all right? So, okay, we know the mass, we know the radius, and each spoke here, this is a 3-spoked wheel. Okay. We know the mass, and we know, in this case, the length is equal to the radius, which I can kind of see in the picture there. So determine the moment of inertia. This one's kind of sneaky. I'm going to give you a second to think about it. So I'll give you 30 seconds to kind of get your brain wrapped around it so I don't go too fast. So go ahead and think about this one, maybe without looking at the solutions, and just think, what the heck is going on? Normally, this is the time I would walk around the room and talk to you all. So I'll try to slow myself down a little bit. And since I'm here, I'm going to go ahead and talk through this. And I know it's not the ideal teaching method, but I'm going to do it. I'm going to split this into a couple of pieces. And maybe you didn't know this. If so, that's cool that I'm talking. I see a ring, so I'll call that I1. And then I want to add to that some other pieces. I see this blue spoke here, this blue spoke here, and this blue spoke here. And for me, maybe you don't notice this, but for me, it looks like each one of those should contribute exactly the same amount to the moment of inertia because they're all stuck there. So I'll call these the 2s and the ring the 1. From experience, I know the following is true. I'm going to get I about the center of mass first. And the idea here is I can figure out, I'm going to forget about this nail up here. I'm going to use this. That's the center of mass in this problem, rather than use this nail up here. The nail I could do at the end using the parallel axis theorem, right? If I could figure out the purple axis, all I need to do is shift everything by a distance of r using the parallel axis theorem. So what am I trying to do here? I'm going to try to look this one up in the table. Then I'm going to try and look these 3 up in the table so that I can figure out the purple one, so that then eventually I can do I parallel is equal to, and I see your chat. I'll be right there, or Trey can try and handle it. Thank you, Trey. Trey is the man. And I'm going to pause for a second. Okay. Okay. So Ryan's question is very good. My apologies, Trey, if you were already answering him. Oh, he is. Oh, my bad. Yeah.
It's fine. It's fine.
You're the man. You're the man. Sorry about that. Yeah. So let's pause for a second, because this is if you could understand this problem, all the rest kind of look like this. So let's really take our time with this one. I'm going to walk through this whole thing again and see if this helps. And then I'll go through and see if Ryan's question is answered. So again, what am I trying to do here? I'm trying to understand this crazy looking object that's the red ring plus the 3 blue spokes. And it turns out from experience, I know the following. First, figure out the moment of inertia about the center of mass. And Ryan, your question relates to this. If I can figure it out about the purple axis about the center of mass, by definition, regardless of the shape, I can always do, oh crap, I want to make sure you got something here. This should be, you have to use the total mass here, which happens to be 4 capital M. In this problem, why is that? Because the ring has mass M and each spoke have mass M. So when you do this, That accounts for the fact that this one is much farther away. And the point that you're asking, Ryan, is the crux of it. This would be almost impossible to do using calculus because it'd be so confusing. Whereas with the parallel axis theorem, it's only moderately confusing until you've done it 100 times. So I definitely want to take a look at the chat and see if this is starting to get you somewhere. Okay. It's much easier to figure out the moment of inertia about the center mass than shift it. The equations are just, it's like doing something in Excel and you have different tables, right? So you do a column for the numerator, a column for the denominator, and then a column for the whole fraction. Sometimes it's easier to split things into parts, or in a computer code, right? Yeah. Okay, good. All right, let's do it. So let's go take a look at this. Remember this picture here. So I'm going to get rid of those annotations now. That's our sketch. Let's go look at the equations and see if it makes sense. So the idea is, and I cannot stress this enough, we're doing the center of mass here. So that's why we can do all three the same. If I do it at the center, now the center is not what was asked for, but it helps me get what I want. This is from the table. This is from the table. Wait, why isn't it 1/12? Because it's a rod at the end. Remember, if it's a rod at the center, I use 1/12. If it's a rod at the end, it's 1/3. And if I go back to my picture, these are not a rod at its center, they're a rod at its end. Okay. Okay. So now when you do that, you get this interesting result. I at the center mass is this. That's cool. So now I have this piece for the parallel axis theorem. And just like I said before, the mass of this thing is not m, it's 4m, and it's all those pieces put together, and that's what gives us this very cool result. So instead of having to do a lot of thought, we do this simple procedure, and you can crank out this parallel axis theorem. Now I know the equivalent rotational mass for this thing if I hang it on the nail. What? Let me show you what I mean. The point of this problem was this. If you take this mass and you hang it on the nail, how is that going to affect its torque, its rotation rate, its blah, 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 blah? Well, now I know. I figured out this thing I, because if you remember, we know sum of force equals MA is suddenly going to shift to this new equation, sum of torque equals I alpha. So if I want to understand the acceleration of an object, I need to know about the mass or the force, something like that, right? If I want to understand the angular acceleration of an object, I need to know this stupid thing that we're spending all this time on. And then if you care, these are vectors, right? All right, that's where we're going with this. I'm going to go ahead and pause for a sec. Okay. Any questions right now?
Yeah, so basically what you were doing in that first part that I was asking the question about, if I got this right, you just took the parallel axis theorem equation and kind of that's an easier way to find the I center of mass and then just plug it in.
So wait, could you say that again one more time?
So basically, if I'm getting this right, what you did was take the parallel axis theorem equation to find the moment of inertia about the axis, which is the nail, right? And
right.
What you did that I was confused about, where you found the rotation about the center of mass, that was finding the part that you need for the equation I center of mass plus md squared.
Right.
Okay.
So you recognize, and Jerry, I'll get to your question in a second. You recognize that, okay, I don't know what the moment of inertia is about the wheel, about that point up at the top. So then I'm like, okay, I know I can get it if I could just get this piece. So I'm going to then get that piece and then do it. Yep.
Okay, cool.
Yep. That's right. So yeah, Jerry. Hopefully that question got answered for you, Jerry. Read the problem statement carefully. It was the wheel was M and each spoke was M. So there's a total of 3 spokes. Yeah, okay, got it. Sweet. Thanks, man. All right. Now I want to show you the 2 most common misconceptions that people have. I used to teach this class in the fall, and so we'd get to this right about Halloween. So thus, look at 10.9. Dracula takes a break from sucking the blood. Yeah. All right. Let's see. All right. So now I'm going to remind you here using the dotted line axis, it says the parallel. Okay. So earlier, just if I go back to this problem, 10.13, the answer to 10.13, where is that? Come on now. Was 1/6. See it there? 1/6. So the answer to that one was 1/6. Okay. So now if I could get back to here, I just wanted to point that out. So earlier we figured out, oh my gosh, come on. When you use this axis, that's the moment of inertia. So I'll call that I red. And now Dracula says, I expect this equation is true. By this equation, I mean this. What is wrong? Why is that not true? Think to yourself. Why can't I just say that this one, the solid one, I get the mass. The distance between them is L over 2. So why can't I do that? Hopefully, I'm going to go ahead and do the answer. Give me a second. The center of mass is 1/3 from the fat end, which is about right here, right? So that's I center of mass. The whole point of the parallel axis theorem is this is not at the center mass. This is not at the center mass. The equation won't work unless you use the center mass. This right here is not, and it's not an axis through the center mass. It's not valid. Now, if you want, you could go back and derive this correct answer and show that it works. Interestingly enough, you might think you need to use calculus, but you don't. So what you could do is, putting this on here again, you could actually use, sorry about that line being so crooked. This is the center mass axis, right? So you could do a parallel axis theorem to get to the center of mass, and then you could do another one to get over here to this other. So you could actually say that I dotted is equal to I center mass plus this distance, which is what? Mass times, I think it's L over 3, because it's a third squared. And then you could do it again to get this way, where this distance in here, this little green distance, I think is L over 6, because a third plus a sixth should equal a half. Whoa, I'm going to go check the chat real quick. Yeah, L over 3. Not sure what you mean, Nate Dog, so that's cool. Hopefully that addressed that question. Okay, got it. Right on. And then, so remember this. One of these has got to be the center mass. That was the point of that. Okay, remember that you can only use the parallel axis theorem if this one right here is at the center mass. Interesting to note, everybody, this is something that can help you remember. because moment of inertia, we use it all the time. Notice that any other axis is bigger than the parallel, as long as the center of mass, moment of inertia, is always the smallest compared to any of the ones parallel to it. So if you go to any other axis, it has to be bigger than the center of mass moment of inertia. Now keep in mind, this also has to be parallel. So yeah, be careful with this. The center of mass moment of inertia is always the smallest compared to any that are parallel to it. And just to make clear how confusing this can get, look at this equation sheet. Notice there are some subtleties here. Look at this one. That is an axis through the center of mass. So is this, right? Doesn't that go right through the middle? And notice that this one is smaller than that one, but these axes are not parallel. This one goes this, the disk. Yeah, okay. So, right, versus these two, they're not parallel to each other. So watch out for that. But in general, try to remember center of mass moment of inertia is the smallest. That's a good thing to remember. Let's do one more of these. Whoa, yowza. There's my summary. Oh, crap. There we go. Okay. Ooh, Frankenstein. Frankenstein's ready to party. Now, consider the uniform disk at right. From the table, if we look in the table, the moment of inertia of a disk is 1/2 mr squared. That's a fact. And then I'm going to use the parallel axis theorem, and I see, okay, then I get 3/2 mr squared. My physics teacher says this is total crap, but whatever. All right. Why is this wrong? Why is that not true? Take a second to think about it. Rhetorical question. You don't have to respond. When I look at the table, there's the disk, right? It's 1/2 for a disk. Whoa. Why can't I just add the mr squared? Here's the deal. Look carefully. This one, it's exactly what I was just saying. This one runs through the middle of the disk's face. Look at our particular equation, our particular question. This one is parallel to this other axis. This one, right? So this one is a 1/4 mr squared from the table. The axis that's 1/2 is this one, coming out of the page and going through it back way like that. So this one is a 1/2. Again, the two most common mistakes people make with the parallel axis theorem, because we have to use it all the time, I really wanted to cover this well. The idea is this. Enough said on this. Make sure that you use one of them through the center of mass, and make sure that axis is actually parallel. I had better stop talking about this before you fall asleep. All right. Questions on that? Okay, so in 1017. In 1017, it's a sphere. A sphere is going to be the same no matter which way you do it. So if you do a sphere, let me go to the sphere. That's tricky, right? This one. So, right, if you go this way through a sphere, or if you go this way through a sphere, right, they all go right through the center, and the sphere is the one object that is symmetric about any rotations. So it has a continuous rotation symmetry, if you're into those phrases. But yeah, so no matter which way you rotate it, as long as the axis goes through the center, that's why, if I can do, in the sphere case, I believe it was like this. And so that works out where, in this case, we just know this distance is r, and I saw the chat pop up. I'm going to check it out. Oh, I see. Gotcha. Yeah. Right on, Jay. And yes, spherical shell as well. So spherical objects are these ones that have what are called continuous rotation symmetry. So if you really want to get into that, just go sneak up to Brian Youngblood via Zoom, because I know that's so easy, and ask him about continuous rotation symmetries and see him get gleeful. All right. The ring in 1018. Let me read the ring, and let's see here. Yeah, great question. The ring in 1018. Take a look. Actually, this one is right, because if I could draw the wheel like this, the idea is this would be the center, and this would be the parallel. Great question. Great question. Right on. Yep. And then, yes. Okay, cool. So notice if I finish that one, let me clear these drawings. Hopefully that addressed that one. So notice the wheel problem of 10.18 is basically this one here. That's what I was trying to get at. Oh my gosh, come on. So this was supposed to be the spokes. And there is, you could see it totally matches this picture right here. So, and now we see the hard part about chapter 10. This is one of the hardest parts, is that no longer can you simply use the mass of an object. You have to know the mass of the object and its axis of rotation and whether it's parallel to the center of mass or not before you can do any calculations. So a lot of times on a test question, the first part of the question will be, what is the moment of inertia, or what is the center of mass? Because if you don't know the center of mass position, and if you don't know the moment of inertia of an object, it's really hard to do some rotational problems. All right. Let's see. Right on, right on. Okay, cool. All right, sounds like you guys know what you're doing. So, and then let me talk a little bit about page 63, and then we'll take a break. All right, I know you're tired, so let's go back to this one. If you care, if you are a mechanical engineer, this term is pretty useful. You will learn more about it in a statics class. All right, so or a dynamics class. I forget which one. Might be dynamics. You will also learn why they use these XX and YY. Why? It's because it turns out the moment of inertia is best described by a matrix for most objects. That's beyond the scope of our course. Perpendicular axis theorem, it's oftentimes an extra credit question on a test. So this particular page is fun to read, but not required for your exam. I want to repeat, if you want to skip something, page 63, you could skip it. But you could see how it might work out and blah, 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 blah. It's only valid for plates in the XY plane. The derivation is there. If you're a math freak, you could see it. It works out pretty quick. It turns out that the moment of inertia perpendicular to the plane is always larger than the moments of inertia in the plane. So yeah, okay, I'm going to stop. Let's stop the share. So this is a good time to take a break. If you want to skip a page, skip page 63. You know what? Just because we're there, I want to do the summary, which is on page 64. Look at the summary of what we did before we take the break. So I'm going to screen share. Okay, so we've talked a lot about it. This is our summary. Identify the axis location. Hopefully you could split it up into parts and just add them up from the table. If not, you might need to use the parallel axis theorem. Remember that the axes have to be parallel and one has to go through the center of mass. If it's a planar object, you could use this. We will not be using this, okay? I guess maybe in theory you could use it, but the only times we need it, you should already have a table. So I don't think you're ever going to need this in my class, but there you go. And then if all else fails, go to these. And like Trey said earlier, if you have a non-uniform density, you kind of have to do that. Some general intuition. When mass is close to the axis, I is a small number. Figure skater arms in, small moment of inertia. What does moment of inertia mean? If you have a small moment of inertia, it's easy to change your rotation. Okay. Moment of inertia is a measure of an object's ability to resist changes in rotation. Mass, you resist changes in velocity. I resist change in omega. For any axis orientation, the center mass is always smaller than any I parallel. And then blah, blah, blah. This is kind of the perpendicular. Okay. I'm going to take a break. If you want, you should take a look at these two. And these ones are pretty good. If you do this one, this is a great practice. And then you can see how do they change? And that's a great conceptual question. So if on the oral exam interviews, if you're curious what type of question you might get asked, it'd be like, let's say this was the test question here. If this was your test question, this might be how I might mix it up. I might give you one of these parts. There's a chat. No, you don't need the perpendicular axis theorem. It's handy, but definitely as an engineer, okay? Not in physics that I know of. Okay, so that's a great question. I'm going to go ahead and stop the live stream, and then we'll come back here. It looks like it's 5:36. I'll come back for more in just a minute.